Hi guys, welcome back to YouTube channel Chemistry Live UGPG. So today we will talk about hybridization. So this will be highly beneficial for BSc Chemistry students under CBCS syllabus. So I have a simple message for you guys. Please think for innovation, be creative, learn everywhere, anytime and help to learn others. So this is the syllabus for Core 1 paper Unit 4 Chemical Bonding. So let's discuss hybridization and equivalent and non-equivalent hybrid orbitals. So let's define what is hybridization. So hybridization is the intermixing of atomic orbitals to give rise to equal number of new hybrid orbitals of equivalent energy, shape and size suitable for the pairing of electrons to form chemical bonds in valence bond theory. So what are the characteristics? So hybrid orbitals undergo better overlap which can form stronger bonds with the other atoms than pure orbitals. It provides stable geometry for a molecule. Generally, hybrid orbitals mostly equivalent. And hybrid orbitals form either a sigma bond or contain a lone pair of electrons. So principle, what is the principle? So linear combination of orbitals of the same atom is called hybridization. And the combination of n atomic orbital generates n hybrid orbitals of an atom. So hybrid orbitals have better directional properties and can form stronger bonds. The hybrid orbitals can form equivalent bonds. So hybrid orbitals are not only orthogonal but also equivalent, which means a symmetry operation of the molecule can transform one hybrid orbital to another. So let's take one example. We know methane has sp3 hybridization. So carbon, the ground state configuration is 1s2, 2s2, 2p2. So carbon in excited state. So this 2s electron will go to another 2p orbital. So the configuration is 2s1, 2p3. So one of the 2s orbital and 3p orbital, they will intermix to give rise to 4 equivalent sp3 hybrid orbitals. So each has one unpaired electron, and we know in methane molecule we have 4 hydrogens, and this unpaired electron can overlap with 1s electron of 4 hydrogen atoms as shown here. So giving rise to 4 sp3 s sigma bonds. So one sp3 1s sigma bond. So we have the structure of methane is explained. So let's talk about the electron pair, shape and bond angle and hybridization correlation. So if the valence shell electron pair is 2, the shape will be linear and bond angle 180 and hybridization is sp. Similarly, if you have sp2 hybridization, bond angle will be 120 and structure will be trigonal planar. And if it is sp3, then bond angle will be 109.28 minute and it will be tetrahedral. And if it is dsp2 or sp2d, then 90 degree and square planar. If it is sp3d or dsp3, bond angle is 120 degree and 90 and trigonal bipyramidal. If it is sp3d2, then bond angle is 90 degree and the shape will be octahedral. And accordingly, the number of electrons pairs are written here. So hybridization is a theoretical process or step in going from an atom to a molecule. So hybridized state never actually exists. It cannot even be detected by spectroscopy. So the energy of hybrid orbitals cannot be measured and can only be estimated theoretically. So there is a misconception that hybridization is the cause of a particular molecular shape or structure. So that we should not think about. Now let's talk about what is equivalent hybrid orbitals. So hybrid orbitals where the ratios of participating atomic orbitals are same for all the orbitals are called equivalent hybrid orbitals. For example, sp3. So for sp3 hybridization, 4 atomic orbitals such as 1s orbital and 3p orbital are involved to produce 4 equivalent sp3 hybrid orbitals. So here 1s orbital and 3 p orbitals, so they will intermix, giving rise to 4 equivalent sp3 hybrid orbitals. So when the molecule is formed, okay, so we have they will be directed to the corners of a regular tetrahedron. So all four new orbitals are equally same sp3 character. So geometry will be regular tetrahedron and bond angle is 10928 minute, bond length single bond. So let's discuss the non-equivalent hybrid orbital. So hybrid orbitals where the ratios of participating atomic orbitals are different or not the same for all the orbitals are called non-equivalent hybrid orbitals. So that is due to the presence of a lone pair of electrons based upon BSE pair model. So for methane molecule, no number of bond pair equal to 4 and number of lone pair equal to 0. So hence all 4 orbitals possess sp3 hybrid orbitals and all are equivalent. But if you take the example of water or ammonia, the central atom has sp3 hybridization. So in ammonia, 3 bond pair and 1 lone pair. And in water we have 2 bond pair and 2 lone pair. So for both the cases, the lone pair of electron bearing hybrid orbital and bond pair bearing the orbital are not equivalent. So in case of methane, it would be tetrahedral and NH3 ammonia has a pyramidal, and in case of water you will have a band structure or V-shaped structure. The next reason is presence of dissimilar atoms rather than the central atom. So in CS2F2, so carbon atom is sp3 hybridized. So 4 hybrid orbitals are not equally sp3 hybrid orbital because 2 CH hybrid orbitals bonds are physically and chemically different than the hybrid orbitals of 2 CF bonds. So instead of bond angle 10928 minute, in reality the HCH equal to 111.9 and CFCF has 108.3. So this is due to the electronegativity difference, that the fluorine has highest 4.0 and hydrogen has 2.1. So with increase in percentage of S character of hybrid sp3 orbital, the bond length is diminished. So bond pair repulsion enhanced and hence the bond angle. Similarly, with increase in percentage of p character of hybrid sp3 orbital, the bond length become larger and the bond pair repulsion minimized and hence the bond angle. So let's talk about in detail what is sp hybridization. So sp hybridization we see in the molecule BeF2. So beryllium ground state 1s2 2s2 and beryllium in excited state will be 1s2 2s1 2p1. So 1 2s orbital and 1 2p orbital. So they will intermix, giving rise to 2 equal sp hybrid orbitals and each contain one unpaired electron. So these two unpaired electron can overlap with the unpaired having the one electron in fluorine atom, 2 fluorine atom, so you get BeF2 molecule. So you have a sp hyphen 2p sigma bonds. So this is the structure, linear structure for beryllium fluoride. So each electron in an atomic orbital can be described by wave function psi. So the combination of s and p orbital giving rise to 2 hybrid orbitals, psi1 and psi2, and may be expressed as psi1 equal to a1s plus b1p and psi2 will be a2s plus b2p. So upon solving the coefficients, you will get psi1 equal to 1 by root 2 s plus px and psi2 you get 1 by root 2 s plus s minus px. Similarly, let's talk about sp2 hybridization. So example is boron trifluoride. So boron in ground state 1s2 2s2 2p1. So boron in excited state will be 1s2 2s1 and 2p2. So one of 2s orbital and 2p orbital. So they will intermix, giving rise to 3 equivalent sp2 hybrid orbitals. And these sp2 hybrid orbitals overlap with fluorine atom, giving rise to 3 BF bonds. So you have a BF3 molecule. So here bond angle is 120 degree and the structure is triangular planar. So the sp2 hybrid orbitals can be formed by combination of 1 2s orbital and 2 2p orbitals and can be expressed as psi I equal to aib plus BiPx plus CiPy, where I equal to 1, 2, 3. So if you solve the coefficients Ai, Bi and Ci, okay, by applying orthogonality condition and normalization condition, we get psi 1 equal to 1 by root 3 s plus 2 upon root 6 into px, and psi 2 will be equal to 1 by root 3 s plus 1 by root 6 px plus 1 by root 2 py, and psi 3 will be equal to 1 by root 3 s plus 1 by root 6 px minus 1 by root 2 py. Similarly, we can have a sp3 hybridization. So example is methane. So carbon in ground state, the configuration is 1s2, 2s2, 2p2. So carbon in excited state, so one of 2s electron will go to 2p orbital. So here 2s1, 2p3. So this 2s orbital and 3 of the 2p orbital, they will intermix, giving rise to 4 equivalent sp3 hybrid orbital. And this sp3 hybrid orbital contains one unpaired electron each, and this will overlap with 1s orbital of 4 hydrogen atoms, giving rise to 4 CH bonds, giving rise to the methane molecule and tetrahedral structure, and the bond angle is 109.28 minutes. So linear combination of 1 2s orbital and 3 2p orbital having same value of principal quantum number belonging to the same atom. So psi sp3 will be AIS plus BIPX plus CIPY plus DIPZ. So I equal to 1, 2, 3, 4. So these AI, BI, CI and DI, they are coefficients. So by applying the both normalization and orthogonality condition, and if you solve for coefficient, you will get psi 1 equal to 1 by 2s plus root 3 by 2 px. Psi 2 will be 1 by 2s minus 1 by 2 root 3 px plus root 2 by 3 pz, and psi 3 equal to 1 by 2s minus 1 by 2 root 3 px plus 1 by root 2 py minus 1 by root 6 pz, and psi 4 equal to 1 by 2s minus 2 root 3 px minus 1 by root 2 py minus 1 by root 6 pz. So please subscribe to our channel Chemistry Live UGPG. This is also available in the website www.chemistryliveugpg.com. For class 11th and 12th, this is the channel Foundation Chemistry AB. This is a simple step towards e-learning, making life better. Thank you all for learning.